Okay, so encryption in keys, you have to start with a readable message. So the whole idea of encryption is that you have a message that you want to send from point A to point B, and if it's intercepted in the middle, you don't want people to understand it. So many modern encryption algorithms make use of keys in some way. Generally, when you talk about keys, you're talking about a public key, which is available to everybody, and a private key, which is available only to the receiver in this case. Those public and private keys are linked by a mathematical formula. The public key is used to encrypt the data, and the private key is used to decrypt the data. Now, there are some cases where it's the other way around, that your public key is used to decrypt and your private key is used to encrypt, and we will have a look at that a little bit later on, but in terms of understanding it, that's a reasonable starting point. Any intercepted data is unreadable, and that is the main aim. So at the point of being sent, you have a readable message. At the point where it is received, you have a readable message, and anywhere in between, you want that data to be unreadable. So any interception of your data during communication is pointless because the intercepted data is unreadable. So what we do is we apply a key to your readable message, and when we apply a key to the readable message, it becomes an unreadable message. Now, as I said, the public key is accessible to everybody, but the public key cannot be used to decrypt the data. So there's a mathematical relationship between the public key and the private key, but they're not the same. And this distinguishes symmetric from asymmetric encryption. Symmetric encryption is where you have the same key. So things like the Caesar cipher, where you have an offset, strictly speaking, your encryption might be +2 and your decryption might be -2. So in that way they are different, but the key, the offset is 2. So really it's the same key being used for encryption as decryption. Similarly, if you're using an XOR, an exclusive OR, on your data, then it's the same value that is being used to encrypt and to decrypt. When you apply an exclusive OR twice, you get back to where you started. In those cases, the sender and the receiver both need to know what that key is. So in this case, when you take that key, the public key, and you apply that to your unreadable message, you still have an unreadable message. Okay, so it's the whole point is that you have two different keys linked mathematically, but not the same. Now, there's a little problem with keys if you think it through. And the main problem is, because the public key is available to everybody, then if you imagine that, for example, your bank were to use this system, anyone could encrypt a message using the public key. So if a bank has a public key and that key is made available to everybody, then everybody has access to the public key. That means that anybody could pretend to be you because they have your public key. That's because your public key is the same as everybody else's public key. So to authenticate data during transfer, we can use a digital signature. And this is where we've got a simplified version of a digital signature and a more complicated version of a digital signature. The general idea, the general concept, is before you send a message, the sender can add a unique value to the code. And that value is a digital signature, much like a normal human signature. When it's received, the receiver looks for the digital signature. If the digital signature is missing, then the data isn't authentic. If it's present, then the data is accepted. So that's the basic concept of your digital signature. The unsimplified version obviously is a little bit more complicated than that. So what actually happens is you take your unencrypted data and you calculate a hash value. So a hash value, or a hash total in some way. This is a value that's calculated from the contents of your message. So a simple hash value is just where you have a particular number. Say you have some invoices and you add up the invoice totals. That overall total then becomes your hash value. Realistically, all of your data is in binary, and therefore you can do whatever calculation you want on any of the data, whether it's text or whether it's music or whatever it happens to be. It's all in binary and therefore can be treated the same. Now, you might see it referred to as a checksum, and you might see it referred to as a hash total. There are a few different terms, and again, all the different terms all mean very slightly different things, but for our context, then they're interchangeable. The hash value, this calculated value, is encrypted using a private key. And this is the digital signature. So when we talk about a digital signature, it's the hash code that has been calculated, and then it has been encrypted. The signature and the message data are then encrypted using the public key. So in this case, if you remember the public key from the bank, and the message is transmitted. The receiver, the bank in this case, uses their private key to decrypt the message. And then the receiver uses the sender's public key to decrypt the signature. So this is where at the start of the video I said the public key and private key may be used for different things. So from the bank's perspective in this relationship, the bank has a private key, which is used to decrypt the message, but it also has access to the public key from the sender, which is used to decrypt the signature. Then the hash value is recalculated, and the hash value is compared to the hash value that has been transmitted. So if the data has been modified in any way during transmission, when that hash value is recalculated, then it will provide a different result, and you'll know that the data has been compromised in some way.